Okay, welcome back. The topic of our class today is this number, n to the n minus 2. Okay, it's some number, but I want to show you that this is a number that appears very naturally in several contexts in combinatorics. So it's a number that we like a lot in combinatorics. And if you ever see this number appear in your research, then you should get excited and remember the class today. So one place where it appears is in the enumeration of trees. So let's talk about trees. So a tree on n is going to be just a. Right, we've talked about trees already. So this is a graph. It's a connected graph. Connected graph on vertices 1 up to n with no cycles. Okay? And let's say that T of n is the number of such trees. Number of them. Okay? So for example, for n equals 4, well, let's do n equals 3 first. Okay? So you need to have 3 vertices. They need to be connected, and you can't have any cycles. And so if you think about it, well, you have to, I don't know, these are the 3 vertices. Then you have to at least draw one edge. You're still not connected, so you have to draw at least another edge. And now you can't draw any more edges because then you would make a cycle, so that means that all trees look like this, right? But they can have any labeling, right? So A, B, C, those are the numbers from 1 up to 3. So how many trees are there? Well, again, remember that when we talk about a graph is an abstract combinatorial object. It's not a drawing. So if I switch the labels of A and C, that is still the same graph. Okay? And so taking that into account, how many labelings are there? Well, I just have to choose who B is. It's either 1, 2, or 3, and then the other guys are determined. So that means that T of 3 is 3. Okay. Let's do n equals 4 real quick. So when we do n equals 4, we're going to see that there's 2 kinds of trees. Either like this, or like this. How many of these are there? Well, again, I just have to choose who's in the middle. Which label goes in the middle? 1, 2, 3, or 4, and then that determines the tree uniquely. What about here? Well, I need to choose the labels of the 4 vertices, and so what I'm going to be choosing is a permutation, right? There's 24 of them. But you see, it doesn't matter if I draw it like this or like this. So there's half of that. So out of the 24 permutations, they double count the trees. Okay, that means that T of 4 is. Oh wait, what? yeah, 4 plus 12. Sorry, I'm having trouble adding today. 4 plus 12 is 16. Okay, and okay, so let me give away the punchline. For n equals 3. This is 3. For n equals 4, this is 16. And so we're going to show that T of n is n to the n minus 2. So how are we going to do that? Well, let me define something auxiliary called a rooted tree. On n is a tree on n with something called the root, with a special vertex, with a chosen vertex called the root. Okay? And so let me say R of n is the number of them. But let me very quickly say that this is almost the same problem, because to choose a rooted tree, you just choose your tree, and then you choose the root, and the root could be any of the n vertices. Right? So R of n is equal to n times t of n. But it's going to turn out that R of n is a little bit easier to compute with the technique that I'm going to show you right now. Actually, the technique is what we were using last time. So we're going to use the symbolic method to count rooted trees. So what's a rooted tree? Well, one way of thinking about it is that you have this special vertex, and then it doesn't really matter how you draw it, but let me just kind of hang it from that vertex. So I don't know. Everything is hanging from that vertex, and what do you have under here? Well, under each one of these guys, you just have a tree hanging from it. So it's kind of a recursive construction. Now, each one of these trees has a special vertex, which is the one that's attached to these guys, right? And so a rooted tree is a root and some rooted trees hanging from it. Or let me say a rooted forest. Hanging from it. And what is a rooted forest? It's just a bunch of rooted trees. Okay? And so in this language that we have been using, so in the language of the symbolic method, rooted trees, let me call them RT, are the same thing as first choosing one singleton, right? And so we call that an atom, and then choosing some rooted forest that hangs from there. So rooted tree with labels is an atom with this product that we spoke of last time. Right? This is the product of labeled combinatorial classes and the rooted forest. Okay. Remember that what this product does is that it says, okay, if you want to put a rooted tree structure in a set, you have to split it into two subsets. On the first subset, you put an atom, and on the second one, you put a rooted forest. Right? Now, if you want to put an atom on the first subset, it has to be a singleton. And so you end up choosing something here which has a label, and then you put a rooted forest structure first. Question?
So the fact that you have that product, that means that the order in which the things appears matters? So because you're choosing some sort of like ordered partition.
Right, so this is ordered where there's an order between the atom and the rooted forest.
Got it.
But the rooted forest doesn't know which tree goes first. These are rooted forest is just a bunch of trees. They don't come in any order. So that's my first equation that I want to write down. But then, what is a rooted forest? Well, a rooted forest is a bunch of trees, a bunch of rooted trees. And so how do we say that? A rooted forest is a set of rooted trees. Right? And so that means that so the exponential generating function for rooted trees satisfies what? Well, it satisfies that it is equal to the product of the one of atoms and the one of rooted forests. The one of atoms is Z times, what's the one of rooted forests? Well, if rooted forest is a set of rooted trees, then remember that these are related by exponentiation. Right? So this generating function is just e to the Z. Okay. This is a little bit unusual, maybe. So what we get is this kind of interesting functional equation that R of Z satisfies. Okay. And it kind of captures the idea that rooted trees are this recursive thing. Okay, so what do we make of this? So let's take this. Let's take this equation and interpret it in at least two ways. So one way is the following. R of z is equal to z times e to the r of z. So let me plug in that r of z is z to the e of r of z. But let me plug in r of z is equal to z to the c times e to the r of z, etc. Probably you've never seen something like this, and analysts will get extremely uncomfortable looking at this. But actually, this makes perfect sense in formal power series. Because at every time we're just taking the exponential of something that starts with z, we can always do that. Now, what exactly does this equation mean? It means that if you take the limit of z e to the z, then z e to the z e to the z, then this, and so on, then that sequence of power series converges, and it converges to this. So this is a very strange formula for rooted trees, and it's a valid formula. It's kind of cute, but maybe it's not so enlightened. I mean, it's not so useful in that it's not going to give us this formula very easily. But I like it. It's a nice formula. What about another interpretation? Well, what I can do is the following. Let me rewrite this equation as z equals r of z e to the negative r of z. Okay? So this means that if I look at the function z e to the minus z, and I take the compositional inverse, I'm going to get r of z. Right? So if I take this thing, and I take the compositional inverse, this is r of z.
What's that?
So compositional inverse means what you should plug in here to get the identity. So what function do I need to plug in for z to get the identity? R of z. This is like sine and arc sine. It's or like 1 over x and 1 over x. It's the inverse function. Okay, but now, well, what does it mean? Well, I think you're right in getting a little bit worried because we haven't really talked about compositional inverses in the ring of formal power series. So this could be a bit of a reason for concern, but maybe let me talk about that in just a second. But what I want to say is this: that this means that what I'm trying to do is find the coefficients of this compositional inverse. Right. So how do I find the coefficients of a compositional inverse? Like this one? Well, it turns out that there is a beautiful theorem in analysis that tells you exactly what to do. And so let me first state the theorem, and then I'll state the hypothesis. Okay, let's first get to the point of like the good news, and then we'll put the disclaimers in. So Lagrange inversion formula. It says that if the compositional inverse, and again, let me make clear that this notation here means compositional inverse. So if I take some formal power series and the compositional inverse exists, then the coefficient of z to the n in that compositional inverse is given by something. Now, it turns out that it's convenient to just put an n here. And it turns out that it's a little bit more general. So not only can I do this for the compositional inverse, but also for any power of it. Okay. But for us, k is going to be equal to 1.
For any natural power?
Any natural power, yeah. So here I'll write for n and k in the natural numbers. So this is equal to k times the coefficient of x to the n minus k in x over f of x to the n. So it's really a beautiful formula. It says that you're able to, oh, I guess these were z's. So this formula says that if you want to compute the coefficients of a compositional inverse, then you're going to be able to do that if you know how to compute the coefficients of powers of z over f of z to the n. So any questions about this statement of the Lagrange inversion formula? Yep.
So when you say, when you put like an n in front, do you mean the coefficient times n?
Right. Yeah, so here I just mean the coefficient times n is equal to this. I could send the n over here if I wanted, but this looks a little bit nicer. Maybe let me just write a quick fact here, which is that yeah.
Can I ask you? I'm still confused about compositional inverse.
Mm-hmm.
Do you have like an easy example?
Give me just a second. So I'm gonna erase this weird formula. So you're asking for another example of compositional inverse. I mean, it's really, so this is the same compositional inverse that you teach your precalculus students. Right? What's the compositional inverse of sine of x? It's the inverse sine function. Or like, what's the compositional inverse of square root of x? It's x squared. And you know there's some issues with where you can plug in or not plug in, and those issues are, you learn about this in analysis, or even in precalculus actually. But it's exactly that. And so what this equation means is that if you take this function, and now if for z you plug in this thing, you get the identity function. So if you plug in r of z times e to the minus r of z, you get the identity function. So actually, if you want to try this out, you know the series of sine and arcsine? Sine yes, arcsine no. Well, this would be a way of finding the series for arcsine. So try it out. Okay, let me just. I want to say that let me just say when this exists. So f of z compositional inverse exists if and only if f of z is equal to a1z plus a2z squared plus etc., where a1 is not 0. In the ring of formal power series. And if it exists, then it is unique, and f inverse of f of z is equal to f of f inverse z is equal to z. Okay. And so this means, like if you want to find the compositional inverse of this, you should be finding some series g, so that when you plug in a1 times g of z plus a2 times g of z squared, etc., you should be getting z. That's what it means. Yeah.
So if f of z has no constant term, what does it mean to write z over f of z?
Well, so f of z has no constant term, which means that this z is going to cancel this z. And you're going to have 1 over something that has a leading term, which is good because remember we can only invert things that start with a constant. So that's consistent. Okay, so let's use the Lagrange inversion formula. So let's use it for, what's our f of z? I guess our f of z is z e to the minus z. And we're going to use it for k equals 1 because we only care about the coefficients of r of z. So we get n times the coefficient of z to the n in the compositional inverse, which is r of z. Right? So this is equal to, when I put k equals 1, I get the coefficient of z to the n minus 1 of z over f of z, which is equal to this, to the n. Right? Now, what's the coefficient of z to the n in r of z? Remember that r of z is the generating function for rooted trees. Right? So this is the number of rooted trees. But remember that this is an exponential generating function. So I get it divided by n factorial. So I get equals to the coefficient of z to the n minus 1, and this over this is just e to the z. Right? And then to the n I get e to the nz. So that looks like it's good news, that this is easy to compute, right? What is this? This is, we know how to find the power series of an exponential, right? It's equal to the sum over, let's say, m greater than or equal to 0 of nz to the m over m factorial, right? This is e to the nz. Remember, n is just a number, and so nz is just our variable. So then what is the coefficient of z to the n minus 1 here? Well, it's what did I get when I put m equal to n minus 1? So I get n to the n minus 1 over n minus 1 factorial. And this is r of n, and then n factorial divided by n is n minus 1 factorial. And so I get that r of n is n to the n minus 1, and since t of n was that divided by n, I get this. Okay. So that's a proof. That's our proof. That's our first proof of the enumeration of trees. Okay. It's kind of magical in some way. And it's really illustrative of the fact that whenever you can phrase your problem in terms of finding the coefficients of some compositional inverse, then you have a very useful tool here. So at this point, you can take 2 points of view on this proof. So, and the point of view depends on whether you trust or you don't trust what I just told you. And let me say it a little bit further. So this is a theorem in analysis. Okay, this is a theorem in analysis, and if it's an analysis, then actually there's a different condition for the inverse, for the composition inverse existing. Really, the hypothesis that you put on the Lagrange inversion formula is not this algebraic condition, but the condition that f is holomorphic around 0. If you remember, if you know or remember what that means. Now, e to the minus z is as holomorphic as it gets, and therefore this theorem does apply. And so that is one way of, through analysis, proving this formula. And then we really would be invoking this theorem in analysis. And then we have to kind of, we keep saying how in this class we don't want to necessarily worry about convergence, but occasionally it's useful, and this is an example where it is useful. Now, the other point of view is to kind of say, well, actually, the other way that you can do this is if you're a combinatorialist and you already know how to prove this, and I'm going to show you another proof of this, then you could just kind of turn this on its head and say, well, what if I try to use trees to prove the Lagrange inversion formula? And it turns out that there is a way of doing exactly that, and understanding that the Lagrange inversion formula is in some sense a statement on the combinatorics of trees. And I'm not really going to go into this in the class, but if you're interested, this is something that Stanley does in the book. So he develops the combinatorics of trees, proves some theorems about trees like this one, and then uses that combinatorics of trees to give a combinatorial proof of the Lagrange inversion. So that's another kind of fun way of doing this. Regardless of which one you like, I think the point is that an answer as simple as this one deserves a better explanation than this invoking the Lagrange inversion formula. This is where your instinct for a bijective proof should kick in. So let me show you a bijective proof of this fact. So bijective proof. So what I'm going to do is count the... So actually, there's at least two very nice bijective proofs, one of which is the more standard one, and the other one I like better. So usually when people teach this, it's more standard to do something called the proofer code, and you should look this up. This is a nice proof. But I want to show you a different bijective proof, which is that I'm going to show that there are n to the n trees with a skeleton. And what I mean by this, what's a tree with a skeleton? It's going to be a tree that has kind of a spine with a beginning and an end. Okay. So you could take some tree like, let me just use this example because I know the bijection is not trivial with this example. Okay, so I might take this tree. Okay, that's a tree, but remember we're counting labeled trees, and so it's very important that I put labels on these. Okay, so there's an example of some labeling that I might have chosen with the numbers from 1 up to 15. And I want to prove that there's n to the n minus 2 of these things. And so what I'm going to do is that I'm going to impose a head and a tail, which maybe we'll use different colors for. So maybe I'm going to say that this is the head, or I guess I don't mean head, I mean like the top of the spine. And let's say that this is the bottom of the spine.
What's like a better definition of skeleton?
So really what I'm doing is that I'm considering trees that are labeled and that have a special vertex that I color blue and a special vertex that I color red. And they might be the same vertex. Okay? So there's n choices for the blue vertex, there's n choices for the red vertex. And so I should get n to the n. But then it's useful to think that once I choose a blue vertex and a red vertex, there's a unique path between them. Right? Because in a tree, for any two vertices, there's a unique path, and so that's what I'm calling the skeleton. So what I'm going to do is this. I'm going to say, well, let me take the skeleton, and I have a very nice bijection for skeleton, for skeleta that have labels on them. So I'm going to take this skeleton, and I'm going to think of it as a permutation of the numbers involved. 1, 2, 4, 6, 8, 9. Go to 4, 8, 6, 1, 9, 2. Okay? This is the permutation that I see on the skeleton. And I'm going to translate it to another way of thinking about this that I like, which is cycle notation, which is that 1 goes to 4, 4 goes to 6, 6 goes to 1, 2 goes to 8, 8 goes to 9, 9 goes to 2. Okay? So I take my tree, I see what skeleton I got. So I take my tree, I choose a red and a blue vertex, I get a skeleton, and then let me take that skeleton and turn it into cycle notation. And just pretend that instead of doing that, I'm going to now have this. Here's 1, 4, and 6. And let's say 2, 8, and 9. Now, I can't just draw them like this because it's a cycle, so it has an orientation, right? So 1 goes to 4, 4 goes to 6, 6 goes to 1. And then 2 goes to 8, 8 goes to 9, 9 goes to 2. So this is very strange, right? But I'm going to do it anyway. So I do this, I turn it into cycle notation, and so I get now that my diagram of my permutation in cycle notation. What do you think I should do with the rest of the tree? I think there's only one natural thing to do, which is to kind of, whatever was hanging from 4, hang it from 4 again. So let me take 4. Now I have 5 hanging from it, and then 13 and 12. Okay. What was hanging from 1? Nothing. What was hanging from 6? 11 and 3. What was hanging from 8? Nothing. What was hanging from 9? Nothing. And from 2 was hanging 10, then 14, 7, and 15. Okay? So I get some picture like this. Now, even if only for aesthetic reasons, this picture is a little bit unsatisfying in that there's arrows on some vertices and not on, there's arrows on some edges and not on other ones. So I'm just gonna introduce arrows on the other edges. Now, if I told you to choose how to orient the other edges, how would you do it? And again, you should just think of something natural that works. So I think there's 2 natural things to do. So I see you going like this, and maybe somebody might go like this. You either point them towards the cycle or away from the cycles. And maybe it's good to kind of remember that this skeleton, that it was green, and now these are my cycles, right? So the cycles are there. And now let me, well, in some sense the choices are kind of equivalent. I'm going to choose to orient towards the cycles. So every edge has a unique path to a cycle. And so I orient everything towards the cycles. And that's what I get. Okay? And what is this? It turns out, so what did I get? I got precisely the diagram of a function f from n to n. What is the function? It's the function that sends the tail to the head. F of 7 is 10, f of 10 is 2, f of 2 is 8, f of 8 is 9, f of 9 is 2. So do we agree that this is the diagram of a function? It defines a function, right? Because for every vertex, either the vertex is in a cycle, and then because it's a cycle, there's something going out of it, or the vertex is not in a cycle, which means that there's a path to a cycle, and then f of the tail is the head of that edge. So this really gives me a well-defined function from n to n. And of course, there's n to the n of these, so this probably means that we're done. This probably means that this is a bijection from these trees with skeleton to these functions. Yeah?
I missed, what gets mapped to 3?
Nothing gets mapped to 3. Which is a very good point, and it's actually the reason that I chose to orient things towards my cycles, right? F of 3 is 11, but nothing, f of nothing is 3. But that's okay because I didn't want my function to be surjective. I don't care. The function could be any function. And so there's no problem if f of nobody is 3. But there would have been a problem if I didn't have, for every vertex, an arrow going out of it. Which is why I chose to do it like this. So this must be a bijection, and then, I don't know, I think to see it's a bijection, the best thing is to let you think about it. Maybe I'll say a little bit about it, but easy to check that this is a bijection. And maybe let me just make some hand-waving argument about why, given any function, you get a diagram like this. Think of any function from 1 up to n to 1 up to n. And let's say that you start with, I don't know, f of 3. So let's say that f of 3 is 4. Okay? Now what's f of 4? Well, it's something. Let's say it's 7. Then I say, okay, what's f of 7? Who knows? 20. What's f of 20? 18. And you see, this is going to keep being a path until f of something here I've already put down. So maybe f of 18 is 4. And if it's 4, then I'm going to close the cycle like this. And then I go next and I say, okay, well, what's f of 2? Maybe f of 2 is, I don't know, 5. What's f of 5? Maybe it's 9. What's f of 9? Maybe it's 18. And once I get to f of 18, then I end up cycling around. And so you just keep doing this. You know, whenever you take a vertex that you haven't considered, then you just start applying f. And eventually you're going to get stuck. And the only way you get stuck is by going around a cycle. And so that means that you get these well-defined cycles, and everything is pointing towards them. So that's the proof. So hopefully you see why this is my favorite proof. I think this is a really cool proof. The proof record is also very nice, but I like this one better. And now you don't have to. Now we don't have to trust Lagrange inversion to see this result. Okay. Cool. All right. Question?
Yeah, so how does this show, what does it show the n minus 2, right?
Oh yeah, so let me go to the end of it. So this argument shows that there is a bijection between trees with a skeleton and functions from n to n. And I know that there's n to the n of these, which means that there's n to the n trees with skeleton. But then I make the argument that a tree with skeleton is a tree with 2 extra vertices, and I have n ways of choosing this one, n ways of choosing that one. So I get that n to the n is equal to choosing a tree, choosing the blue vertex, and choosing the red vertex. And therefore T of n is n to the n minus 2. I should say that I'm only scratching the surface of combinatorics of trees. This is a much deeper topic. I know some of you were in my course in half algebras and half monoids, and there's a lot of connections there. And if you remember, we proved the Di Bruno formula in the context of half algebras. The Di Bruno formula is very closely related to what I just did. And so if you know what that means, you might look into it, and I think it's very interesting. But yeah, I'm only scratching the surface of trees, and I'm gonna move on to something else right now. And it goes like this. So now we're gonna consider the problem of parking functions. So it goes like this. You have a one street road. You have a bunch of parking spots. Okay, there's 1 parking spot, 2 parking spots, 3 parking spots. And that's it. The road's over. Maybe let's make it curve over here. Okay, so the cars are maybe coming in here. So here's 1 car, 2 cars, up to n cars. Okay. There you go. There's my little cars. And let's put numbers on them just so that we remember which is which. And let's put numbers on the parking spots so that we remember which is which. Maybe this is some like Emeryville Mall or something. It's one way, and maybe there's a shop in front of each one of these parking spots. Okay, and each one of these cars is headed to a particular shop. Okay, so maybe this guy is headed to shop A1. This guy is headed to shop A2, and this guy is headed to shop AN, where these are the shops. There's 1 shop here, 1 shop here, 1 shop here, etc. And so these numbers, so car I is going to shop AI, where AI is some number between 1 and n. Okay, and so they go in. And they're optimistic drivers, and they're all convinced that they're gonna get the spot right in front of their shop. Okay, so what they do is that if you're headed for shop number 5, then you're gonna go for the spot number 5. If it's open, you park there, and if it's not open, you keep driving until you find an open spot. Okay? So they try to park. So he tries to park at AI, and if it's taken, then it finds the first available spot. Okay? And so the question is, given this sequence A1 up to AN, is this going to work out or not? Are they going to be able to park or not? So, can they park? I don't know, let's say there's something really drastic here, like maybe here you end up hitting the highway and the next exit is way in like Fremont, and then they don't really want to go back to the mall anymore. Okay? So there's only one chance to park. If they don't park, then game over. Okay? So, example, what if my vector a1 up to an is equal to 3, 2, 3, 1, 2. Okay, so what ends up happening? So there's 5 cars, 5 shops. So let's see what happens. So car 1 drives in and tries to park in spot number 3 and gets it, right? So maybe I'll label these 1, 2, 3, 4, 5. Let me move the labels here. So these are the labels of the parking spots, or equivalently of the shops. Okay. And now let's bring the cars in. So the cars are blue, right? So the first car tries to park in spot number 3, and it's available, so parks there. The next car number 2, goes for shop number 2, and that's available, so they park there. Then car number 3 comes and goes for spot number 3, that's taken, and so they go to the next one available, which is this one. Then car number 4 comes for spot number 1 and gets it. And car number 5 goes for spot 2, it's taken, this one is taken, this one is taken, so they take this one. And it works out. And so therefore this is a parking function. Okay? But this isn't always the case, so maybe we can do another example like 4, 3, 3, 4, 1. So let's think about what happens there. So in this case, car 1 goes for spot 4, car 2 goes for spot 3, car 3 goes for spot 3, it's taken, this one is taken, so they take this one. Car 4 goes for spot 4, taken, 5 is taken, and then they end up in the highway and it's all over. And so therefore this is not a parking function. Okay, so is it clear what parking functions are? Okay, so the question is when this works out, when this doesn't work out. So why is it that it didn't work out for that second set of preferences? The issue can be pointed at right here. These 4 cars these 4 cars can only park in spot 3, 4, or 5. Right? And I cannot park 4 cars in 3 spots. And so this right here is a certificate of why this was not going to work out in the first place. Okay. So that's an argument for why, if you are a parking function, then I must have at most how many AIs that are bigger than or equal to k. Or let's say bigger than k. Well, bigger than k means that you have to take spot k plus 1 up to n. There's only n minus k available spots, and so there must be at most n minus k cars that are going for those spots. And this is the same thing as saying that I must have at least k 8 i's which are less than or equal to k. This is equivalent. So that argument shows that if a is a parking function, this is true, but I claim that actually this is an if and only if. So that's the only thing that can go wrong. If you don't have that then everybody's going to be able to park and there's no problem. And maybe, yeah, I'm not really going to prove this. This is going to be this exercise. Okay. But this shows that there is a description like this. And let me say that equivalently, reordering the AIs to get B1 less than or equal to B2 less than or equal to etc. less than or equal to Bn, then I must have what? Well, bk is the kth smallest number, and if I have at least k numbers that are less than or equal to k, that means that bk should be less than or equal to k. Okay. And so this is equivalent to saying that if I take my preferences, in this case they are 1, 2, 2, 3, 3, when I put them in increasing order, those numbers should be less than 1, 2, 3, 4, and 5 in that order, less than or equal. All right, and so this allows us to compute the number of parking functions for n equals 3, let's say. So for n equals 3, what are the parking functions? Well, let's first write them in increasing order. And so the numbers in increasing order have to be less than or equal to 1, 2, and 3, which means they could be 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 2, or 1, 2, 3 in increasing order. Okay? And then I get the reorderings of this. So I get 1 plus 9 plus 6, 16. This is the number of parking functions. And it just so happens that 16 is 4 n to the n minus 2. And so this is going to be the case in general, that the parking functions of length n, the number of them is n to the n minus 2. Let me point out something interesting. Okay, let me point out two interesting things about this. First, I think it's interesting that whether you're a parking function or not does not depend on the order that the cars come in. Right? These criteria show it. So if 1, 2, 2 is a parking function, then right, if there's one car headed for store 1 and 2 cars headed for store 2, it doesn't matter what order they come in. Either they're always going to be able to park or they're not going to be able to park. Which I think is pretty surprising that it doesn't depend on the order, but it's true. Another thing that's interesting about this is that the number of categories that I have here, the parking functions come in 5 categories. So what's the sequence that contains the number 5? There's a lot of sequences that contain the number 5, but one of those sequences is the Catalan numbers. And 5 is the third Catalan number. And this is not a coincidence. So that's another nice exercise to show that parking functions come in categories like this, where the number of categories is Catalan. Okay.
What did you say was the number of parking functions?
The number of parking functions, in this case is 16, and what I'm going to state is that in general, it's n to the n minus 2.
But n has 3.
Oh, n plus 1 to the n minus 1. Yeah. So the theorem, there are n plus 1 to the n minus 1 parking functions of length n. Okay. Now, actually, as I was going down the elevator, I thought of a question that I don't know the answer to that I think is interesting, and that maybe the answer is known, but I don't know it, and I have thought about this. So anyway, I think it's worth exploring, which is that we have a function that goes from parking functions of length n to permutations of the cars, right? Because if this is a parking function, if you do get to park, then your parking is going to be a permutation of the cars. Right? For every parking function, you get a permutation of the cars. So what is this map? And what can you say about it? So study it. I have a guess for what this map is, which is that there is, so I think some of you have studied the braid arrangement of hyperplanes, and within it, or related to it, is something called the Xi arrangement, which is some arrangement of hyperplanes, such that, actually maybe let me, well, no, maybe I don't have time to say it. Maybe I'll say it in the forum. That there is this geometric context of hyperplane arrangements where both parking functions and symmetric functions appear, and permutations appear, and there is a natural geometric map from parking functions to permutations there. And I don't know if this is the same map, and I think that's interesting. If it's the same map or not the same map, I'm not sure. Anyway, I think that's a nice question to think about that I don't know the answer to. If you do think about it, keep me posted. Let me know, and we can see if this is in the literature or not. It probably is actually, but I'm not sure. Anyway, what I want to do is prove this. I want to prove this theorem, and to do that, again, there's several proofs, but I'm going to do a bijective proof. And the thing that's a little bit kind of unsettling about this, it's a little bit strange. I mean, it feels like you should make n minus 1 decisions, each one of which should have n plus 1 options. Right? n plus 1 times n plus 1 times n plus 1. But it's strange because each car has only n choices. Right? So it would be more natural if the answer was n to the something. But the answer is n plus 1 to the something, which is kind of strange. Yeah. So I'm going to do something a little bit strange, which is that I'm going to introduce an extra parking spot. And I'm going to do that because there's n plus 1 here. There's only n spots, so let's just introduce an n plus first spot, and let's see if we can make something useful of this. Where do we introduce it? I'm going to give them a second chance to park. So let's introduce it right here. Here's a parking spot. N plus 1. And if it doesn't work out, we're going to actually let them cycle around. But I have to keep going in this direction. Right? I have to keep going in this direction. And I'm going to play the exact same game except that now, okay, so same game, except that if you don't find a parking spot, you just cycle and you keep going. So you're now allowed to cycle around. So if you didn't find a parking spot, then you take n plus 1, and even if that's taken, you can keep going until you find the first spot over here. Okay? And so you see, in this case, everybody's going to be able to park because there's n plus 1 parking spots and there's n cars. So everybody's going to park. And I'm also going to allow cars to prefer shop or parking spot n plus 1. Okay? So what is the number of parking preferences? Preference functions. Well, each car is allowed now n plus 1 options, and there's n cars. So I get n plus 1 to the n, which is almost what I want, except that I want n plus 1 to the n minus 1. And so what do I want to show? I want to show that the fraction of parking preference functions that works is 1 over n plus 1. And so what I'm going to do is that I'm going to take all the parking preference functions and I'm going to put them into groups of n plus 1 so that in each group there's going to be exactly one that works and the other ones don't work. So how am I going to do that? Well, notice that if a parking preference function a1 up to an, what happens when you run it? You let the cars run, and there's going to be one spot that is open. Leaves spot I open. Then what's going to happen when you add 1 to each preference? Well, you see, what's going to happen is just that every car now doesn't want to go to where it wanted to go, but it's going to go to the next spot over, which means that every car is going to end up parked one spot over from the previous one. So if in this preference function car I ended up in spot bi, then now it's going to be just 1 over at bi plus 1, which means that if this preference function left the parking spot I open, then for the next one, it's going to be I plus 1 that's open. Now you might have a complaint about this, which is that I can't always add 1 to my preference, because if a car preferred n plus 1, now I can't let it prefer n plus 2. But then I'm just going to make my preferences go modulo n plus 1. Modulo. And then if I continue this, then, okay, well, a1 plus 2 up to an plus 2 leaves spot I plus 2 open, and I keep cycling through, right? Plus 1, plus 2, up to plus n. a1 plus n, up to an plus n. That leaves spot I plus n open. Okay? And so here I have a group of n plus 1 parking preferences. Which one is the parking function? Get a group of n plus 1 parking functions, sorry, n plus 1 parking preference functions. They're not necessarily parking functions, and in fact there's exactly one that's a parking function. Which one is it? It's whichever one leaves spot n plus 1 open. Exactly one of which leaves spot n plus 1 open. Okay. Now you might say, well, but the rules changed. So is the new game equivalent to the old game? Well, what I have to say to that is that if you left spot n plus 1 open, that means that nobody preferred spot n plus 1. If somebody preferred n plus 1, they would have taken it. So if nobody preferred n plus 1, that means that, so no one preferred spot n plus 1, okay? Which means that the parking preferences were between 1 and n. But now the question is, okay, but I changed something else in the rules, which is that I am allowed to cycle around. So did anybody cycle around? Well, nobody cycled around because the only reason you cycle around is if you passed n plus 1 and that was taken. So if n plus 1 was never taken, that means that nobody ever had to go around. Cars never went around. And so this is a parking function, an honest parking function. Okay. And so let's go back. We said that there's n plus 1 to the n parking preference functions for the new game. Now I split them into groups of n plus 1. Right? It's clear that each parking preference function is in exactly one of these kind of cyclic groups, which means that a fraction of 1 over n plus 1 of them work for the new game. So this is the number of parking functions that work for the new game, but those are precisely the ones that also work for the old game. And so that's the proof that the number of parking functions is what I said it is. The end of the proof. Okay. Cool. Any questions about that? You might. Let me give you a little bit of food for thought here. This shows how parking functions are related to Catalan numbers. Now, what is the Catalan number Cn? We have a formula which is this one. Right? Now let me point out to you that actually in this class we have not proved this formula bijectively. Which is a pity because it looks like a bijective formula. It looks very simple. And it's interesting that this formula involves dividing by n plus 1, which seems very unnatural in these kind of Catalan problems, where things have length n, not length n plus 1. But here I have a setting in which the Catalan numbers fit very naturally into a situation that does have an n plus 1. And so I invite you to think about how this can be used to also explain this formula. And the other thing that I want to, okay, so maybe let me write this. So is there a bijective proof like this one? It's related to this. And then the other thing that I want to point out is that the number of parking functions of length n, these guys are in bijection with the trees. Let me just spell it out. So parking functions of length n are in bijection with trees on n plus 1. Right? We just proved this. And again, it's a little bit strange because these things want to have length n and these things want to have n plus 1 things involved. But so this should bring up the question of whether there is a nice natural bijection between these objects. And in particular, as we saw about transferring statistics from one object to another one, maybe you can show that a statistic on trees corresponds to a statistic on parking functions. And there is at least one very nice bijection like this. And so, yeah, I encourage you to look at that. I think I actually put this in the list of projects as a possible thing to look at. Maybe the last thing I want to mention is that I am going to put a project suggestion involving the connection between parking functions and this hyperplane arrangement called the Xi arrangement. So there's an interesting open problem about that I'm going to be posting there. So I invite you to look at it. Okay. So I think that's all that I wanted to say about that.